Hello, welcome back. I'm Jason with mathandscience.com. The title of this lesson is called Writing Quadratic Equations When We're Given Their Roots. And this is part one. We're actually going to have 4 parts to this topic. Here in the beginning, I'll explain the concept. We'll work a couple of quick examples to get you comfortable with what it is. And then the following sections will increase the complexity so that you can get a lot more practice with more complex problems, but they're all going to be utilizing the basic skills that we learn here. And I'm actually really excited to teach this lesson because what we're going to do is learn about a theorem in algebra that usually is thrown at you in a book. It usually has a box around it or something, and you have to use it. But most students have no idea where it comes from. And so just like everything else that's just thrown at you, you think that you're just supposed to use it, and you end up forgetting about it. And that's how a lot of students think algebra is just a bunch of black magic because they don't really know where things come from. So what we're going to do is we're going to learn how to use this theorem, but we're also going to learn where it comes from. And here's what we're going to learn in a nutshell. You all know that with these quadratic equations, they can oftentimes cut through the x-axis. We call those the roots of the equation. Where y is equal to 0, those are the places along the x-axis where the function cuts through. We call that the roots. And we know how to solve quadratics to find the roots. We can factor them, and find the roots of the equation. We can use the quadratic formula and find the roots of the equation. In this lesson, we're going to go backwards. We're going to go the exact opposite direction. What I'm going to do is I'm going to give you 2 roots. All right, 2 roots. I might tell you that root number 1 is 3 and root number 2 is -5. And from the roots, and only from the roots, what we want to do is reconstruct the parent quadratic equation that has those roots. So let me say that one more time. I'm going to give you 2 roots, and then your job is to come up with the quadratic function that has those roots. All right, so in order to understand how that works, what I want to do is go the other direction first, the direction that we have done a lot. So let me go ahead and review a couple of things, and then we'll show you where it comes from, and then we'll generalize the theorem and do an example. All right, so let's start with what everybody knows how to do. Everybody knows how to do this because we've covered it so many times before. So we already know how to solve this type of quadratic. Let's say we have x squared minus 6x plus 5. And that equals 0. So right now we're just solving this quadratic. And by the way, when we solve it, what we're saying is this quadratic is a parabola of some sort. We know it opens up because this is a +1. It's a quadratic. And if there are any crossing points of this quadratic to the x-axis, we set it equal to 0. We set the equation where we set the y value equal to 0. So when we factor and solve this guy, we're finding the crossing points where this equation crosses. So typically the way that we do that is we factor the thing, all right? And so we say, or we try to factor. It's not always factorable. It's not always factorable, but we're going to try to factor it initially. So we have an x squared term, so we know we have to have an x times an x. And the only way to make 5 with multiplication is 1 times 5. And the only way to get the plus here and the minus here is to have a minus and a minus. Make sure you agree with me. X times x is x squared. This is -x. This is -5x. That adds together to give you the -6x, and then these multiply together to give you +5. So that's the factored form. And so from this factored form, we've done this a million times. We know that x minus 1, this term can be equal to 0, which means that one of the roots is that x is equal to 1. And we also know that this term can be equal to 0, which means that this root is 5. So what it means is that if we were to plot this function, now we take away the 0, f of x is equal to this. It's going to create some parabola. These 2 numbers are the crossing points. It's where the parabola cuts into the x-axis in those 2 locations, that x is equal to 1 and x is equal to 5. We call those numbers the roots of the equation. Also, you can see them referred to as the zeros of the equation. It means the same thing. All right? So what we have done is we've gone the forward direction, because we have already done this kind of thing. We've gone this direction where we have given the equation, figure out what the roots are. Now we want to talk about that we can go backwards. And by backwards, what I mean is if I give you in a problem. So I want you to kind of forget that we've done this now, but I'm going to give you a problem. Given that the roots of some quadratic, some parabola, is x is equal to 1 and x is equal to 5. I'm choosing the exact same thing we've done here because we're familiar with it. Then find a quadratic with these roots. All right, so how do you think you would do it? Obviously, we know the answer. We know that this is the answer, but how do we, if all we are given is this, that these two roots exist, how do we figure out what that quadratic is? And here is the secret sauce of what you do, to generalize what you do. If you know that the roots exist, right, then what you do is you say that the quadratic is going to basically look like this. It's going to look like x minus 1 times x minus 5, and that's got to be equal to 0. How do I know that? I'm not copying this from what I've already done up here. What I'm saying is that if you know the root is 1, and you know that when you solve quadratics, you always get them in this form, like x minus 1, x minus 5, then you know that if the root is 1, this term has to be a minus 1 because that's what you would set equal to 0. And that's how you would get a 1 as a root. And then you know that the other term multiplied by it must be x minus 5 because that's the only way I could get a root of 5. So going backwards is a simple matter of taking the roots that I have and writing the factored form directly from the roots. And you can always do that because every quadratic that can be factored is always going to be some parentheses times some parentheses. And if you know what the roots are, you can always fill in what those parentheses are because those are the roots. That's what you would calculate as the roots. So it has to be x minus 1. That would give me a root of 1. It has to be x minus 5, and they have to be multiplied together. Now, this is not the answer you want to circle. This is just the starting point. Now what we do is we multiply all this stuff out, which we, of course, have all done before up above. But let's multiply x times x is x squared. This term gives me negative x. This outside term is negative 5x. And this term is positive 5. Of course, it's still equal to 0. And then I'm going to go ahead and finish it off here. This is going to be negative 6x plus 5 is equal to 0. So this is the quadratic. So this is the answer. Pretend that we had never done this first part of the problem before. I'm only showing you this so that you obviously are working with something in your mind and you can see that it makes sense and it's real. But the real problem would be everything you would never have known about this above. You would say, well, I only know these two roots are here, so I'm going to have to put this in, multiply it all out. This is the quadratic. So I would know that this quadratic, that's what the quad means, this quadratic has roots of 1 and 5. X is equal to 1 and x is equal to 5. And this is the answer that you would circle, right? Or you could take away the 0, but anyhow, when you set it equal to 0, that's what the roots are basically going to be. Now, here, that part was, I think, pretty easy to understand, right? Because you can take any roots, you can write the factored form directly from the roots, multiply the whole thing out, and that is always going to give you a quadratic that has those roots. However, there's more than one quadratic that can have the same roots. In fact, there's an infinite number of quadratic functions that can have roots 1 and 5, just as an example. So I can pick any two roots I want, any two roots, and I can always find a quadratic by this method, but then there's always an infinite number of other ones that are related to that one that have the same roots. And let's just see how that is the case. So we know that this is a quadratic that has roots 1 and 5. But think about it, this thing is equal to 0. So what I could do is I could take this guy and I could say, okay, x squared minus 6x plus 5 equals 0, right? And remember, this is an equation, equals 0. I can take and multiply anything I want to this equation. Let's multiply it by 2. But if I multiply it by 2 on the left, then I have to multiply it by 2 on the right. And when I do that, what am I going to get? I'm going to get 2x squared minus 2 times 6 is 12x. Plus 2 times 5 is 10. And on the right-hand side, it's still equal to 0. Now, this quadratic is different than this one. I mean, it's completely different. It's multiplied by 2. All the numbers are larger, right? But this quadratic still has roots 1 and 5. So you see, you can take the original one that you find, and you can multiply it by a number. In this case, we just picked 2. And you will get another quadratic that has exactly the same roots. And just to bring it home, let's go back. Let me grab another color here. Let's go back to the original quadratic that we had. Let's say we start out with x squared minus 6x plus 5 equals 0. I can multiply, let me give myself some room. I can multiply this quadratic by, let's try 3. So if I multiply by 3 on the left, I got to multiply by 3 on the right. So if I do that, what am I going to get? I'll get 3x squared minus 3 times 6 is 18x. 3 times 5 is 15 plus 15. Again, equals 0. This quadratic, if you graph it, looks different than this one, which looks different than this one, but they all have roots 1 and 5. So this quadratic is another one that has roots 1 and 5. So you might ask yourself, let me actually catch up and make sure I've done the math correct. So we have 2x squared minus 12x plus 10. We have 3x squared minus 18 plus 15. That's all correct. Okay, so we have three quadratics that I have found that I'm claiming all have the same roots 1 and 5, and I found them just by multiplying by the number 2 and the number 3. So you might imagine I can take that original quadratic I found, I can multiply by 4, I can multiply by 5, I could also multiply it by negative numbers. I can multiply the whole thing by -2, or -10, or -100. I could multiply by 1/2 on both sides, and I'm still going to have the roots, the same exact roots, because if you think about it, if you were to solve this guy and figure out what the roots are, what are you going to do? Well, you're going to first factor out of 3, which is this step, and then you're going to factor this expression, which is going to factor to this, but you're going to have a 3 out in front. So I would divide away the 3, because I would divide by 3 and divide by 3, so it would disappear, and I would have exactly the same root. So for any of these equations, when I factor out the number, I'm left with the same kind of like child polynomial behind, which will have the exact same roots of 1 and 5. That's why there's an infinite family of roots, because I can take an infinite family of quadratics that have the same roots, because I can take the original one and I can multiply by anything I want, all the way up into as close to infinity as I want to get, and I'll get another quadratic that has the same roots. So I want to take a second, and the reason I'm going over this is because the theorem that we're going to talk about in just a minute when I get there will talk a little bit about this multiplication stuff, and it's much easier to understand in terms of numbers than it is in terms of a theorem like that. So let's go and see how is it possible that we can have quadratics that look so different but have the same roots. All right, so we said that this quadratic, the original one, had roots of 1 and 5, and the original quadratic was x squared minus 6x plus 5. That was the original one. So let me go over here and say this is x is equal to 1 and this is x is equal to 5. So the original quadratic, I'm just going to do my best to sketch it, okay? It's not going to be perfect, so forgive me, but it's basically going to look something like this. It's going to go through this point, it's going to reach a minimum, it's going to go up through 5, something like that. It's not exact. I never claimed to be an artist, but this is basically it. And that equation is the very first one we found. So this is basically, how do I want to annotate it? Let's go, I'll do it like this. I'll say, I want to stay away from everything. You'll see why in a second. I'll do this. I'll say f of x, the function, is x squared minus 6x plus 5. So red goes with red, right? This is the equation. Now the second one that we found was this one, 2x squared minus 12x plus 10. We said that when that was equal to 0, that was a quadratic also. So notice, what is the difference between these two? Obviously the numbers are different, but we know it's a quadratic. We know it opens up because they're both positive in front of the x squared term. And remember, the bigger the number in front of x squared means it closes up more. Like if you get larger and larger and larger numbers of that first coefficient, it gets more and more narrow. So that second one has exactly the same roots. It's going to look something like this. It's going to go down like this and something like this, right? And let me just double check my, where am I going to write it? I guess I'll do it here. And the second one will be f of x is equal to 2x squared minus 12x plus 10. So blue goes with blue. And as you might guess, the third one, what was the third one? It was 3x squared minus 18x plus 15. So there's a 3, so it's basically positive, opens up, but it's even more narrow than the previous one, and it has to have the same roots as well. So of course I can't draw it exactly, but it's going to go through and have the exact same roots and come up something like this. Of course the shape of it is not right, but you get the idea. So f of x for the third one is 3x squared minus 18x plus 15. Let me take this away, plus 15. So green goes with green. So now you can see how this idea of finding a polynomial or finding a quadratic with the roots 1 and 5 is really kind of a weird question, because there is not just one quadratic that has these roots. There's always a family of quadratics. I'm going to use the word family, an infinitely related family. These guys are basically the same quadratic, but because we multiplied by a number to generate the family, they have basically the same characteristics. They go through the same roots, but if I were to factor any one of these guys, I'm just going to pull out the number. I'm still going to have the factored form in there. I'm going to have the same exact roots for all of them, but obviously they're getting steeper and steeper. And if I have another one where it's 100 and as a first coefficient, that thing's going to be really, really, really steep and go off of my chart here, but they're always going to go through the same exact roots. So when a problem says find the quadratic that goes through these roots, it's really kind of not true. There's an infinite number of them. So if you find one of them, you've satisfied the problem, but there's always more that you could find just by multiplying the equation through. So just to bring it home, we could say something like, in general, so we can generalize this, in general, we can take a number a and we can multiply it by that base equation, x squared minus 6x plus 5. That's the one that we found the first time. And anytime I take this guy and multiply by any number a, it always has roots 1 and 5. And the number a here that you multiply by determines the shape of whatever particular parabola that you have. So most books are not going to go through a talk like that with a specific example like this. Most books are just going to show you the theorem. And the theorem is going to have a lot of letters, and it makes people dizzy because they don't understand what it means. They don't have the big picture before they look at the theorem. But now that you have the big picture and you understand what it's trying to say, now I'm going to present the theorem as you might see it in a textbook, and you'll understand a lot more how it works and why it works. All right, so this is not going to be so scary. So we're going to generalize this to the following thing that you might see in a book. Given roots of a polynomial, or roots of a quadratic, however you want to say it, r number 1 and r number 2. So it's in terms of r1 and r2 because I'm generalizing it. Any two roots. In that example, it was roots 1 and 5. But r1 and r2 could be any two roots. -3, +7, whatever. It doesn't matter what the roots are. We're going to call them r1 and r2. If I knew that I had this guy, two roots, 1 and 2, how would I find the polynomial? Well, what did I do? I took these two roots, I wrote them in the factored form, and I multiplied it out. That's how I got this equation. And then once I got this equation, I knew that I could multiply by these whole numbers to generate the family of equations. So I'm going to do exactly the same thing here. I'm going to write the factored form. I'm going to do it in a different color. If I have two roots, r number 1, r number 2, then I could say that the equation x minus r1 times x minus r2 has to equal 0. This will be the polynomial. How do I know? Because if I were to get a polynomial factored into this form, then this one would correspond, moving this over, would correspond to r1 root. This one would correspond to the r2 root, exactly as the problem that we have already done. And now we can multiply this out. X times x is going to give you x squared. This times this is negative r1x, so negative r1x, right? This one here, don't forget the negative sign, is negative r2x. And this guy here, negative times negative is positive, r1 times r2. So that looks ugly. See why this gets kind of confusing when you look at it in a textbook, because they got all the r1s and r2s everywhere. But bear with me, we're going to simplify it a little bit. This middle term has a common factor of x. So let's just factor out that. X squared minus, I'm going to pull out the x. And actually, do I want to pull it? Yeah, I want to pull it out like this. Then on the inside, I'm going to have r1 plus r2. And this last term is going to stay the same. Make sure you understand that. Why did I change it to a plus? Well, because I pulled out basically a minus x. And so when I multiply it in, this times this gives me negative r1x. Multiply then this and times this gives me negative r2 times x. So you have to always go backwards and make sure. That's why I needed a plus sign there, was because I actually pulled out a minus x to begin with. And now one other small change is this term. I just want to flip around how I've written it here. So let me switch colors to something else, and I want to write it like this. I'm going to put the minus sign, but this term I'm going to flip it around. I'm going to write it as r1, whoops, did the wrong thing, r1 plus r2 times x plus r1, r2 equals 0. So all I did was, since they're multiplied, 3 times 4 is 12, and also 4 times 3 is 12. Flipping it around doesn't matter. So these are multiplied, so I just flipped the order of them. That's all I've done. Now, you might look at this and say, oh my gosh, this is crazy. What does this mean? All right. What this means is that if I give you roots r1 and r2, right? r1 and r2, then all you have to do to figure out the polynomial or the quadratic that has those roots is stick it into this equation. It's already built. You stick R1 in and R2 and you add them together, and that's going to be in front of the x term. And then these two, R1 and R2, are multiplied together. And then you have a polynomial. You have x squared minus something times x plus some number. That is a quadratic. That is a polynomial that will have roots R1 and R2. Okay, so I'll put this on the side. This is a quadratic, has roots R1 and R2. R1 and R2. So this is exactly the same. I'm actually going to do it. I'm going to go ahead and do it with the example that we've had. But this is exactly what we have already done, but totally generalized. We took the roots, we wrote them in the factored form, we multiplied it out, and we collected terms. That's all that we have done here. So if you know R1 and R2, just stick it in here, and this will give you the polynomial. But you also have the idea that this is actually a family here. So this is the base one, I guess you could say. Or we know that we can take this polynomial of x squared minus R1 plus R2 times x plus R1 R2 equals 0. We can take that polynomial, let me go ahead and stick this a little bit farther over, and we can multiply the whole thing by some number a. And that will generate the family of polynomials. Why did I not multiply it on the right-hand side? Well, I did, but it's 0. So if I write a times 0, it's still 0 on the right, just like it was over here. When I multiplied by 2, then I multiplied 2 times 0, it still was 0. Multiplied by 3, it's still 3 times 0 and 0. So you see, really you only have to multiply the left-hand side because the right-hand side is going to be 0 no matter what. So the idea is, this is the family with roots R1 and R2. So really this is the answer to, this is the theorem that you'll see in a textbook. A textbook might say something like this. They might say, given a polynomial has roots R1 and R2, this generates a quadratic function with those roots, and this other term here can generate a family of quadratics that all have the same roots. So that's what it is. But the first time I looked at it, a long time ago, I was very confused. Like, why is there an A here? Why isn't there only one answer? Why is there two answers? And so I had to do the other example to show you that the base one comes from just, putting the roots in there and multiplying them out, but I can multiply that quadratic that I get by anything I want and still have the same roots because of what I've drawn here. Now, there's kind of an easier way to remember this. This is an ugly equation, I'm not going to lie to you. So easy to remember. I'm going to write that down. Easy to remember. Or easier to remember. Remember it like this. A times x squared minus, instead of all this stuff, remember this as the sum of the roots that you're given. And you have to multiply by x. And then plus the, I'm going to write here, product of the roots given, right, equals 0. So this is a little bit easier to remember. If you think of it in terms of sum of roots and product of roots, sum of roots and product of roots, then really what you have is you have x squared minus the sum of the roots times x plus the product of roots. And that's your base equation, and then I can multiply that base equation by any number I want to generate the whole family of other equations. Because oftentimes what's going to happen, that we're going to find as we solve problems, is when we take the roots and we put them in there and we multiply them out, we might oftentimes have fractional coefficients for the polynomial. That's going to be a correct polynomial, but oftentimes we don't want fractional coefficients, so just multiply through by any number you want to clear all the fractions away, and you'll get rid of them. So this theorem is telling you can generate the base quadratic, and then you can multiply that by anything you want to basically clear any fractions away or get rid of terms that you don't want. As long as you multiply, every term by some number a, it's still going to have exactly the same roots. So now what I want to do, right underneath this, and I'm going to solve a separate problem on the other board, but I want to do it right underneath this while it's fresh in our mind. I want to apply this guy to our example when we have roots 1 and 5. So let's say I give you and I tell you that root number 1 is 1 and root number 2 is 5. And I say, give me a polynomial that has, or a quadratic function that has both of those as the roots. And then you would come back to your theorem and say, well, yeah, I can multiply by a, but I'm just going to take a equal to 1 right now and just use the basic one. So I'm going to say that it's going to be x squared minus the sum of these roots. The sum of these roots is 1 plus 5, so let's leave it as 1 plus 5 now, times x. And then plus the product of these roots. The product is 1 times 5, so 1 times 5. Right? And I'm hopeful that this is going to work. So I have x squared. Here I have minus 6x plus 5 equals 0. And that is exactly what we have. It's exactly what we did. Right? So there's two ways to do all of these problems. You can take the roots, you can put them there, and you can multiply it all out, and you can get the answers. Or you can just use what the theorem is telling you, because it comes from the same place. Sum of roots, product of roots, follow this guy. All right? Now we're going to close the lesson out with one more quick example, and then we're going to move on to the next lesson where we have, a lot more examples where, the problems are a little more complex, more fractions to deal with, other little things you have to worry with, but ultimately we're just going to be using the same theorem over and over again. All right, so let's say we want to find a quadratic with what we call integral coefficients, meaning, whole number coefficients, where the roots of this guy are at x is equal to 2 and at x is equal to 5. Those are the roots of some guy, and we want to figure out what the quadratic, or what a quadratic with integral coefficients are. So the first thing you should do is you want to find the sum of the roots and the product of the roots, because that's what's in the equation that we have there. So if you want to figure out what the sum of the roots are, it's just 2 plus 5, which is obviously 7. And then the product of the roots is just 2 times 5, which is 10. So now that you have the sum of the roots and the product of the roots, you just have to put your equation together. X squared minus the sum of the roots times x plus the product of the roots equals 0. And then if you want, you can multiply that by some number a and generate a different one. But you don't often have to, but you could. So the quadratic function is going to be this: x squared minus the sum of the roots, r2, times x, plus the product of the roots equals 0. So we have x squared minus the sum of the roots we already figured out was 7, so it's going to be 7x, plus the product of the roots, which was 10, which was equal to 0. So x squared minus 7x plus 10 equals 0. So this equation already had integral coefficients. The problem statement here is find a quadratic function with integral coefficients. But what if the roots were weird? What if the roots were 1/2 and 3/10? Well then, when I do all of this sum and product, I'm going to get fractions for all of these coefficients. If I get fractions for the coefficients, this theorem tells me that I'm free to multiply this equation by any number I want. Because multiplying both sides leaves the right-hand side unchanged. I can multiply by anything I want and still have the same roots. So if I did a different problem, like I will here in the future, and I got, like a 1/2 in the front, like 1/2 x squared, when I did all this math, if I got a 1/2 here, I don't want a quadratic with 1/2 as a coefficient. I want integral coefficients. But if I did get a 1/2 here, then the theorem tells me I could just multiply the whole thing by 2, which would clear the denominator and clear the 1/2 fraction. And I would have to multiply by 2, multiply this by 2, multiply this by 2, multiply this by 2, and then I would have a new quadratic that would have exactly the same roots, and it would have integral coefficients. Now this is using the theorem, okay, which I want you to do. That's why it's here. But there's another way to do it. I don't want you to ever forget that. Another way. Actually, it ends up being the same way, but there's another way to do it. If I know the roots are 2 and 5, then I can just build the thing like this: x minus 2, x minus 5 equals 0, because these would be the roots 2 and 5. And I can multiply this and get x squared minus 2x minus 5x, and then the last guy's plus 10. And you can see right away this would be x squared minus 7x plus 10 is equal to 0, which is exactly the same thing. So when you do these things, and of course I could multiply this by any whole number I want to get another quadratic that has exactly the same roots. So when you do these problems, you're going to do them the same way. You can either build them like this and do the multiplication out, or you can just remember the theorem and remember what it tells you and just plug in the values. I'll probably do a little bit of a mixture as I solve most of the problems. But if you ever get a quadratic back as an answer that has like a fraction in it, just multiply the whole thing through by whatever the denominator of that fraction is to clear it out, and you will be guaranteed to have a resulting polynomial with exactly the same roots as the parent. because they all form a family as we've drawn on the board here. So make sure you can solve all these problems. Make sure you understand the concept. Most of all, I want to make sure you understand this theorem. Given roots R1 and R2, this is how you generate the family of quadratics that has those roots. And then follow me on to the next lesson, where we will get practice solving more and more complicated problems of this nature.